going to introduce our software debloating framework called PacJam. Modern software is built and deployed in a one-size-fits-all manner to maximize code reusability and productivity. This has made the use of software packages and package managers very common. But even though developers build software this way, different users need different subsets of features. This results in software bloat on users' machines. Several techniques have been proposed so far for removing or customizing code artifacts. Unfortunately, despite all the benefits of security, software debloating has not gained widespread use yet. We argue that a debloating technique must satisfy a number of criteria to become practical. First, it must provide a configurable fallback mechanism. Second, it shouldn't require complete specifications. And finally, it must not require additional runtime support. None of the pre-existing techniques meet all the desired criteria at the same time. What's more, none of the existing techniques provide support for automated rapid security response. This is a huge problem because there is usually a considerable delay between the public disclosure of vulnerabilities and the issue of patches. To address the mentioned problems, we propose to debloat programs at the package level using a framework called PacJam. PacJam not only removes statically unreachable packages, but also dynamically unused ones using an application tracer. PacJam achieves this by using shadow packages in place of debloated ones. Shadow packages have the same interface structure as the original packages, but only contain a small piece of code that performs management tasks. Here's an overview of PacJam. It takes as input the metadata of the application to be debloated, and it only installs the required packages and uses dummy shadow packages for all the other dependent packages. These shadow packages do not provide any functionality, but maintain the application binary interface to satisfy load time requirements. The first piece that PacJam maintains is the dependency graph. PacJam maintains the information of all the dependencies between packages, both direct and indirect. In VLC, for example, there are 479 dependent packages overall. They are reachable from its 10 direct dependencies. Among them, 324 packages are identified as reachable from VLC using a sophisticated static analyzer. The second component is the usage scenario database. PacJam captures application features by observing which dependent packages the application uses under each usage scenario. We construct a usage scenario database for each application from various available sources. For VLC, we collected around 300 media files to include as many supported media formats as we could. Among VLC's 155 dependent packages, only 134 packages are exercised for playing all the collected media files. These usage scenarios are used to eliminate dynamically unreachable packages. Suppose the user wants to install VLC. PacJam installs only 134 packages and uses shadow packages for all the other dynamically unreachable ones. Another important database in PacJam is the shadow package database. For each package, PacJam generates shadow and sanitized versions along with the original package. The shadow package is a stripped-down version and does not provide original application functionalities. It contains a stub that allows seamless execution of the application in cases where the code in the corresponding original package is required. PacJam installs shadow packages for all the debloated dependencies of an application. This way, the application has significantly smaller attack surface at runtime and does not load extra packages. In the VLC example, the system initially installs 134 packages to support all the usage scenarios. For the remaining 187 packages, it installs the shadow versions. The last piece of the puzzle is post-deployment policy. If an input requires the execution of a shadow package, a stop in the shadow package loads the sanitized version of the package and propagates execution to it. Suppose a new vulnerability is discovered, and PacJam finds that the vulnerable package is libebml. In this case, auto-respond informs our package installer about this package, which will be disabled by replacing it with the corresponding shadow version and also setting a flag in the shadow package database. If a user plays a mkv file, which requires libebml, the shadow package forces the program execution to safely stop the first time a function in libebml is invoked or passes the execution to its sanitized package. Shadow packages are configured to force the program execution to stop, so any security vulnerability in uninstalled packages are prevented. PacJam enables continuous security dependency lifecycle by integrating with vulnerability databases or discovering systems such as CVE databases, GitHub security alerts, or OSS files. Although the initial debloating improves security by preventing zero-day attacks in removed packages, new vulnerabilities in previously safe packages could continue to be discovered. In this case, systems that protect then deploy are unable to respond promptly to newly discovered vulnerabilities. End-day attacks require system admins or developers to immediately respond or fully disable the application until the patch is uploaded. PacJam bridges the gap between these two extremes. Because PacJam does not require modifications to an application, users can post-deploy disable a vulnerable package by removing it from the system and replacing it with the corresponding shadow package. This way, instead of completely disabling the application, we simply remove a dependency and a subset of the functionality as a result. As discussed earlier, PacJam traps executions into this disabled package and safely exits the application. When the vulnerable package is patched, users can re-enable this functionality by installing the patched package and removing the shadow package from the system. Let's take a look at the evaluation results. We evaluated PacJam on 10 widely used Linux applications. To reflect various use cases for each application, we selected test cases from multiple sources such as online tutorials, Stack Overflow, and so on. Our package vulnerability database contains information about each package's known vulnerabilities that are collected from CVE databases. First, we measured the effectiveness of static debloating. On average, PacJam removes 58% of packages across all the applications. This number is significantly less than the number of actually installed packages by the baseline. Interestingly, most of these statically unreachable packages are part of an application's indirect dependencies. For example, Git directly depends on libcurl, which is librtmp. Even though Git requires libcurl for SSL connection, it does not use the streaming protocol provided by librtmp. While one might blame a developer for the vulnerabilities and code bloat within their application, these results suggest that much of the responsibility lies beyond the developer's direct control. PacJam can debloat applications further by removing dynamically unreachable packages with respect to a given set of use cases. We deploy PacJam in strict mode and an initial installation with the union of all the dynamically reached packages. We observed that the average number of dynamically unreachable packages across all benchmark applications is 66%, which is an additional 8% compared to statically unreachable packages. For example, in Git, from 29 potentially reachable packages, PacJam discovers that another 4 are dynamically unreachable. Unlike before, these packages implement features that some users might need, but they can be removed safely for most users without adversely affecting the functionality. For instance, one of these packages provides Kerberos authentication support that most Git users do not need. PacJam reduces the attack surface further and results in an overall reduction of 46% of total application bugs and 69% of gadgets. On closer inspection of the CVEs, we further notice that 30% of these bugs are among high-impact bugs. Next, we measured the fallback overhead and compared it with the state of the art. We deployed VLC with all packages as shadow packages. Then we ran it with the complete set of use cases. PacJam loaded on demand any required package during execution. VLC encountered around 2 milliseconds delay on each test case. This delay constitutes only 0.01% of the running time on average over all the test cases. For each test case, the delay VLC has is proportional to the number of debloated packages required to execute the test case. This can be observed by few spikes on the VLC pack line, which is the blue line, and it indicates that the corresponding test case required a debloated package to load. The first test case itself loads most of the required packages. Once VLC reaches a stable state, we encounter only a small delay that is due to the initialization of the data structures required by the policy. Piecewise, on the other hand, has a relatively higher overhead of roughly 32 milliseconds in every invocation of the application. This overhead is around 2% of the running time. This is due to the need to walk through the dependency graph even if the corresponding library is not used during runtime. In other words, Piecewise failed to keep many of the dynamically unused functions out of memory. Besides, Piecewise is susceptible to soundness issues in static analyzers because it does not provide any fallback mechanisms. Finally, we evaluated the effectiveness of auto-respond to rapidly respond to unpatched vulnerabilities. Auto-respond handles unpatched vulnerabilities by disabling the packages that contain them. However, disabling the required packages affects the application's usability too. To evaluate this effect, we measure the reduction in functionality when packages containing vulnerabilities are disabled. We gather all the high and critical CVEs along with the corresponding package information. For each of these packages, we instruct PacJam to replace the package with our shadow package and measure the number of scenarios that terminate the execution after flowing into a shadow package. We repeat this process for each CVE of each application. In Git, for instance, 95% of the CVEs affect less than 5% of the functionality. In Firefox, 78% of the CVEs do not affect any of its functionality. But there are certain CVEs, disable the packages, they will affect 100% of applications' functionality. Anyhow, even though the functionality reduction is high, we argue that this would be only for a short duration as vulnerabilities in commonly used libraries are usually fixed. To recap, we presented a package-oriented debloating framework, PacJam, for adaptive and security-aware management of an application's dependent packages. PacJam enables package-level removal of security vulnerabilities in a manner that minimizes disruption to the application's desired usage scenarios. Our experiments on a suite of 10 widely used Linux applications demonstrate that PacJam can effectively debloat applications and provide rapid response to newly discovered vulnerabilities in already installed packages. Thank you for listening.